We did Lab 2, Newton's second law, and our question is, how will changing the net force on the system while keeping the mass constant affect the acceleration of the cart? In Lab 2, students study Newton's second law, net force is equal to mass times acceleration. We were asked to determine how changing the net force on the system, the cart, pulley, string, and the mass, affects the acceleration of the cart. Our claim is that the greater the net force is, the greater the hanging mass, the faster the acceleration of the cart will be. This is because, according to Newton's second law, acceleration is equal to the net force divided by mass. The greater the numerator is in this equation, the greater the acceleration will be. We already know that the study subject, the cart, weighs 0.441 kilograms. We hope that this experiment will give us a deeper understanding of Newton's second law.
The materials needed for this lab are a laptop with SparkView, a motion sensor, a lab notebook, a flat metal track, assorted masses, a low-friction pulley, and string. The independent variable for this lab is the net force exerted on the cart, which was measured by the amount of hanging mass on the string. The dependent variable is acceleration of the cart, which was measured by a motion sensor and an application called SparkView that graphs the motion of the cart. We controlled this experiment by making sure the total mass of the system was always 0.60 kilograms. This is the procedure we followed to do this lab. Step 1. Set up the Chromebook and SparkVue. Step 2. Place the track on a flat table with the pulley extending past the table. Step 3. Place the motion sensor on the track across from the pulley. Step 4. Place the cart on the track with the string hanging over the pulley. Step 5. Choose a system mass to keep constant and distribute between hanging on the string and in the cart. The sum of the hanging mass and the cart mass must always add up to the chosen system mass. Step 6. Tie a mass to the string and place the remaining mass from the system mass in the cart. Step 7. Turn on the motion sensor and let the cart go without making the mass swing. Step 8. Use the graph from SparkVue to determine the acceleration of the cart. Step 9. To increase the net force, take some mass out of the cart and place the same amount on the string instead. Step 10. Release the cart for 3 trials and record the acceleration every time the net force is increased. We changed the net force 6 times with 3 trials each, so we had 18 trials total. Step 12. Calculate the average acceleration for each set of 3 trials to create a scatter plot using Excel. Step 13. Use the scatter plot to determine how changing the net force of the system affects the acceleration of the cart.
Overall, this lab was based on Newton's second law. Through this lab, we were trying to determine the effect hanging mass had on the acceleration of the cart. In Activity 1, we learned that by varying the net force and keeping the total mass system constant, we can see Newton's second law firsthand. Here we learned that the acceleration of an object is produced by a net force that is directly proportional to the magnitude and is in the same direction. However, it is inversely proportional to the mass. So in order to get a stalled car moving, there needs to be a force exerted on the cart. Because there is a change from a position of rest to motion, the change in velocity is vi equals 0 and vf equals v for acceleration. Throughout this lab, the main equation was F net equals mass times acceleration. However, for this specific cart, there were 2 main equations. The first one was the F net of the cart was tension, or the mass of the cart times the acceleration of the cart. The second equation was the F net of the hanging masses, or the mass of the hanging mass times gravity minus tension. In this equation, the F net of the cart is the total force on the cart in the horizontal or x direction. T is the tension in the string, and mc, which is the mass, affects AC, which is the acceleration. To find theoretical acceleration, we use the equation A theoretical equals the mass of the hanging mass divided by the mass of the hanging mass plus the mass of the cart times gravity. Our data proves that the greater the net force exerted on the cart is, the faster the car accelerates. Some problems we experienced were when we released the hanging mass, it swung back and forth, causing errors in the graph of the chart's acceleration. We solved the problem by holding the mass while releasing it. Another problem was that the cart would suddenly change direction and move either to the left or the right instead of going straight. We fixed this by checking to make sure that the cart was straight before releasing it. Also, we kept the mass of the hanging weight less than 250 grams to prevent the cart from accelerating too fast. We also kept the mass of the hanging weight above 30 grams because anything below that exerted minimal force on the cart, causing it to move extremely slow. Another factor that may affect the way that our data was presented was in the intervals that we increased our weights. One reason we believe that the acceleration was lower than expected was because the friction of the pulley would have acted upon the tension of the string. Because the pulley was neither massless nor frictionless, it could have affected the acceleration greatly. Also, human errors such as exerting pressure on the hanging mass or technical errors such as the sensor losing the cart could have changed the acceleration of the cart itself.